Hi, and welcome to our lecture on the law of sines. We're in the midst of our study of trigonometry, and if you go way back in the beginning, you'll remember we defined the trigonometric functions using right triangles. Well, in this lecture and the next, we'll focus on oblique triangles, that is, triangles that don't necessarily have right angles. And we'll try to what's called solve them. And solving means the following. Given certain parts of that triangle, you try to find the remaining parts. And there are two main theorems for this as a tool for solving these triangles. The law of sines, which we'll study in this lecture, and the law of cosines. Let me make a side comment about the law of sines. If you've taken a physics course, you might remember Snell's law, and this law of sines will look familiar to you. Also, let me add that the law of sines and the law of cosines, next lecture, are not directly used in calculus courses except when doing applications of calculus. And many of the applications of calculus involve triangles where you have to use the law of sines and cosines. So how does the law of sines work? It's a beautiful theorem. It's really neat how it sets up. Imagine the following triangle. We'll label it ABC using capital letters for the vertices, and we'll label the opposite sides using small letters. So sides A, B, and C are opposite angles A, B, and C. Okay. The law of sines says the following. A certain equality of ratios. The side A divided by sine of the angle at A equals side B divided by sine B equals sine C divided by sine C. It's a beautiful theorem, isn't it? The ratios are always equal to each other. And of course, you could write it in reciprocal form. Sine A over A equals sine B over B equals sine C over C. And the bottom line is here, given three values, you can actually find the fourth by solving this equation for the missing value. As we go along, we'll also see some interesting difficulties in using this law. Some subtleties will arise. But let's do a simple example to get started and build up some confidence. Here's a triangle, and we will use the law of sines to find the remaining sides and angles. We will solve this triangle. Here's the setup. The triangle again is labeled ABC, and the angle at A will be 25 degrees, the angle at B will be 60 degrees, and the side opposite A 12 inches. So we're given three pieces of the triangle, and the goal is to find the other three pieces. Angle at C, that's missing, side B and side C. Okay. Well, it's pretty easy, I think, to find the angle at C. If you know two angles of a triangle, the sum is 180 degrees, so we can find the third side. So clearly, if A is 25 and B is 60, then C is 180 minus 25 minus 60, or 95 degrees. So we now have all three angles of this triangle. By the way, you might have noticed that we're using degrees in this lecture, and that will probably be true for this lecture and the next. One tends to use degrees when trying to solve triangles. So let's use the law of sines to obtain the value of side B. B over sine B equals A over sine A. That's a piece of the law of sines. Solving for B, we have B equals A over sine A times sine B. Plug in the values. A is 12. Angle A is 25 degrees, so the denominator is sine of 25 degrees, and all of that is times sine 60 degrees, the sine of angle B. And then on a calculator, you punch all that in. You should be in the correct mode, of course, in degree mode, and you obtain about 24.59 inches. And then you do the same for side C. A over sine A times sine C. Plug in the numbers, 12 divided by sine of 25 times sine of 95. Punch it on your calculator. You obtain about 28.29 inches. And we've solved this triangle approximately. We have to deal with approximations in this lecture and the next. And you see that we have all three sides and all three angles. Let's do a quick application. kind of a fun application. Suppose you have a pole that's tilting towards the sun at an angle of 8 degrees from the vertical. So here's the vertical, the pole's kind of tilting this way, and it casts a 22-foot shadow that way. And suppose also that the angle of elevation from the tip of the shadow to the top of the pole is 43 degrees. How long is the pole? Here's a picture, and I've drawn the following. I've drawn the pole at an angle of 8 degrees off the vertical, and I've labeled that side A, and that's what we're trying to find, isn't it? The angle A, which is the angle of elevation up to the top of the pole, that was given to be 43 degrees, and we're also given that the vertex A is 22 feet from B, the foot of the pole. So we're trying to find little a, and we know side C, because C is the top of the pole, and we know angle at A, and do we know the angle at B? Aha! Well, if you form a right angle, then the angle at B is 90 plus 8 degrees, or 98 degrees. That would be the full angle at B in the triangle ABC. So let's go ahead and do the arithmetic now to solve this problem. A is 43 degrees, B is 98 degrees, and of course now we know angle C, it's the difference, 180 minus 43 minus 98, or 39 degrees. And by the law of sines, A over sine A equals C over sine C. Solving for A, we have C over sine C times sine A, 22 over sine 39 times sine 43, comes out to be about 23.84 feet. That's how long the pole is, this slightly tilted pole. Let me make some comments now about solving triangles. If you're given two angles and a side, then things are really nice because you can immediately find the third angle because the sum is 180 degrees, and then you can use the law of sines to solve the other two sides. So angle, angle, side, or angle, side, angle, those are easy cases. It's more complicated if you're given two sides and an angle. Today we'll look at the case of two sides and an opposite angle, and that will be interesting. And then in the law of cosines lecture, next lecture, we'll look at the case of two sides and the included angle, or in also all three sides. Suppose you're given all three sides, can you solve the triangle? That will be the law of cosines. All right, let's do, again, a more interesting example. Here's the setup. A will be 22 inches, B will be 12 inches, and the angle at A, 42 degrees. So here I've drawn the picture. A is 42 degrees. The angle at A is 42 degrees. The angles at B and C are unknown. The side opposite A is 22, and the side opposite B is 12. Let's solve this triangle. Okay. We use the law of sines. Sine B over B equals sine A over A. So sine B equals B times sine A divided by A. Plug in the characters. 12 sine 42 over 22 equals approximately 0.36498. I did that on my calculator, of course. All right, so here's one of the interesting points. We know what sine B is. What's B? Well, we have to use the inverse sine key on our calculator. Knowing the sine, can we find the angle itself? And it turns out to be about 21.41 degrees. And then angle C would be the difference of the two known angles, 180 minus 21.41 minus 42. So C's a large angle, 116.59 degrees. And finally, the only missing character is side C, A over sine A times sine C. Plug in those numbers. I think you're getting the picture. 22 divided by sine 42 times sine of 116.59, and that yields about 29.40. So you see in the picture again, C is the largest angle, and the side opposite, of course, is the largest. Okay. Let me show you an example now that's quite interesting to me. It's a triangle that we'll try to solve, and we won't be able to, and wait to see why. Let's try to solve the following triangle. Suppose A is 15 inches, B is 25 inches, and the angle at A is 85 degrees. Here I've kind of attempted to draw a picture. There the angle is 85 degrees, and the side B is 25, and the side opposite A is 15, but I haven't extended it all the way. You'll see in a minute why. Let's try to use the law of sines in this setup. Sine B over B equals sine A over A. So sine B is B sine A divided by A. Plug in. Here we go. 25 times sine 85 divided by 15. Punch it on my calculator. What do I get? 1.6603 approximately. The sine of B is about 1.66. Uh-oh, that's bigger than 1. There is no angle B such that the sine is bigger than 1. No such triangle exists. Isn't that an interesting case? So you can't just arbitrarily throw down some numbers and expect to get a triangle. There's no triangle with these dimensions. All right. Let's now show what I think is the most interesting case. And remember what interesting means in my mind, the most difficult case. Here we'll see some data that gives rise to two possible cases. It's really interesting how you can get two triangles out of this data. So here's the setup. We've got A to be 2, B square root of 12, which is about 3.4641, and the angle at A is 30 degrees. So there's the setup. A is 2, B is the square root of 12, and the angle at A is 30 degrees. All right. Let's use the law of sines, of course. Sine B over B is sine A over A. So sine of B will be B sine A over A. We know all three characters. Square root of 12 times sine 30 divided by 2. And that turns out to be 2 square roots of 3. Now I know the exact value of sine 30. Sine 30 is a half. Let's pause there for a minute. Sine of 30 is a half. That dates way back to our beginning lectures on trigonometry. I'm not necessarily using a calculator on this, although I could, and it would give the answer of a half. But this is one of the angles we know. The sine of pi over 6, or 30 degrees, is a half. And that's all divided by 2. Do some cancellations, and you're left with sine B equals square root of 3 over 2. Okay, sine of B is square root of 3 over 2. Let's go back to some fundamentals. Can you think of an angle whose sine is square root of 3 over 2? And again, this is one where we know the exact values. Sine is square root of 3 over 2. Right, 60 degrees. The sine of 60 is the square root of 3 over 2. Bonus question. Can you find a second angle less than 180 degrees? Because we're talking about a triangle here. Can you think of a second angle that has sine square root of 3 over 2? Right. 120 degrees also has sine square root of 3 over 2. Now, you wouldn't get that using the inverse sine key on your calculator because it would only give back the first one. But in terms of triangles, there are two angles floating around here, 60 degrees and 120 degrees, and both satisfy the equation sine B equals square root of 3 over 2. So what does that mean for us? That means that we have two possible triangles that meet the criteria of this data. We have two triangles. Let's explore each one in turn. Here's the first one. A is 2, remember. B is square root of 12. The angle at A is 30. That's true for both triangles. But now the angle at B is 60 degrees. Here's a picture of that situation. See, the angle at A is 30. Square root of 12 is one side. 2 is the side opposite angle A. And it turns out that because B is 60, C is 180 minus 30 minus 60, or 90 degrees. The angle at C is a right angle. This is a right triangle. Isn't that cool? So what's the side opposite angle C? Well, we can use the Pythagorean theorem. We don't have to be fancy. We can just go square root of 12 squared plus 2 squared, and that equals 16. Square root of 16 is 4. Now we have all three sides. Square root of 12 and 2 are the legs, hypotenuse 4. And by the way, what's the angle at B? 60 degrees, and in fact it adds up to 180. Okay, we've solved this triangle. But remember, there was a second solution here. It turned out that the angle could also be 120 degrees at B. So here's a picture of that situation. Again, the angle at A is 30 degrees. The side opposite is 12. The angle at B is 120, and the side is still the square root of 12. So let's finish off the problem. A is 2, B is square root of 12, angle is 30 at A, angle is 120 at B, so C equals the difference, 180 minus 30 minus 120, or 30 degrees. Isn't that interesting? The angle at C is the same as the angle at A. We have an isosceles triangle, don't we? Oh, okay, so the side AB, the side opposite angle C, is 2, equal to the other side of 2. And so this is a second triangle that satisfies the original data. And if you superimpose this triangle on the previous triangle, you'll see how they fit together. This is the so-called two-case situation with the law of sines. And you have to be careful when this happens, that you might have actually two triangles that meet the original setup. Okay, why don't you be the teacher for a moment? Let's pause here for a moment, because that was a pretty hard example, I think. Why don't you be the teacher? Student comes up to you and says, "Oh, I really like this law of sines, Professor. Can I even use it on right triangles? Is it okay to use the law of sines on right triangles? Because up to now, we've been kind of using it on what I used to call oblique triangles, where all the angles are kind of weird. They aren't 90 degrees necessarily. So would it be okay to use it on a right triangle?" Well, I think so. In fact, let's see what happens. Here's a right triangle, ABC. I put the right angle at C in the usual labeling. What would the law of sines tell us about this situation? Well, let's look at A and C. Sine of A divided by A would be sine of C divided by C, and C is 90 degrees, so it's sine 90 divided by C. And what's the sine of 90 degrees? Oh yeah, that's 1. So that's 1 over C. And solving now, moving the A to the other side, you have sine A equals A over C. Let's look at the picture again. Sine A equals A over C. Wow, that's the original definition of the sine function, opposite over hypotenuse. So sure, you can use the law of sines on a right triangle, but you could also use basic trigonometry on a right triangle. It might be a little bit easier. All right. It turns out that the law of sines has lots of applications. As I mentioned, it's related to Snell's law in physics. It also can be used to develop a fairly convenient formula for finding area of triangles. You're familiar with the usual formula, area equals 1/2 base times height of a triangle. Well, let's develop a different formula. It's kind of neat. I think you'll like it. So here's the setup. Here's a triangle, ABC, our usual setup in this lecture. And let's drop the perpendicular from vertex C down to the side AB, down to side C. And that we'll call the altitude or the height of our triangle. So what's the area now of this triangle? Well, it's 1/2 base, which is C, times the height H. Okay, can we get a formula for H? Well, let's use our definition of trigonometry. Sine A is H over B. Sine of A is opposite over hypotenuse. And now we have that the height would be B sine A, moving the B to the other side, and the area is 1/2 base times height, which is 1/2, the base is C in this triangle, and the height is now B sine A from that derivation we just did. And so the final answer is 1/2 BC sine A. Let's look at the picture. The area of that triangle is 1/2 the product BC sine of the included angle. It's the product of two sides and the included angle. Well, the sine of the included angle. And this would work, by the way, for any triangle and any angle that you happen to know. Kind of a neat formula, kind of a surprising formula. The area of a triangle is pretty simple. The product of two sides times the sine of their included angle, all divided by 2, of course. Okay, let's do an application. Here's a triangular lot. It's got an angle of 102 degrees. And if you march this way, it's 52 meters that way, and it's 90 meters that way. So it's a triangular lot, and you know the included angle, and you know the lengths of two sides. By the way, my home in Gainesville, Florida, has a triangular lot. I'm not sure the dimensions are exactly as given here, but it basically looks like this. It's kind of a sharp corner there, and it's got a dimension this way and another distance this way. Well, given this triangular lot in the picture, we can find its areas using this fancy new formula. So, what's the formula said? It says that the area is 1/2 AB sine C. Who are these people? A and B are the two sides, and C is the included angle, so it's the sine of C, again, all divided by 2. So let's plug in the numbers. It's 1/2 times 90 times 52 times sine of 102 degrees. Punch that again on your calculator, and you would get approximately 2,288.87 square meters. Okay. Have you been to Italy? Even if you haven't been to Italy, you've probably seen pictures of the Leaning Tower of Pisa, a fascinating piece of architecture, a fascinating tower. It leans. It's kind of off to an angle. And here are some statistics about it. It turns out that its length, the height of this tower, if it were standing straight, is about 58.36 meters. But it's leaning, and it's leaning at a distance of 5.45 meters off center. Here I've drawn a picture of that situation. You can see the tower, and it's not standing up straight, but it's leaning, and that lean is 5.45 meters off center. Okay. The question is, what's the angle of the lean? How much is the angle of the lean here? All right. Another question, of course, which has always sort of puzzled me, why is it leaning? What happened to it? You might remember that, or might have read that the soil is unstable under the Leaning Tower of Pisa. It's kind of a mixture of clay and sand and water, and over time, after it was built, it slowly began to lean. And I don't know if it's going to fall over one day. I know they've done lots of work to try to keep it steady and not lean too much. A long time ago, I walked up the tower, and it was a frightening experience because of the lean. As you stare down from one side, it's kind of scary. I don't think I would do it again if I were in Italy. But again, here's our picture. We've got our angle alpha that I've labeled that we're trying to find. And we know that the tower is 58.36 meters high, but it has that lean of 5.45 meters. Can we find the angle alpha? Well, this problem actually is fairly simple, isn't it? We don't have to use that fancy law of sines for it. We can actually find that angle by the simple definition of the trig function. Can you think of the appropriate trigonometric function to yield the angle alpha. What do you think? Well, what's the sine of alpha? It would be the opposite divided by the hypotenuse. And the opposite is 5.45 meters, and the hypotenuse is 58.36. Plug those into your calculator, and you'll obtain something like 0.0934. Now use the inverse sine button and use it in degree mode, and you'll obtain the answer of about 5.36 degrees. So that's the degree measure of the leaning Tower of Pisa. Kind of an interesting result. Okay, I hope you found this lecture fairly straightforward. I think using the law of sines is not too hard. Given 3 pieces, you can find the 4th. But then we noticed some interesting issues that came up. One was it's possible that no triangle exists. But much more interesting are the cases where the data might yield 2 possible triangles, and hence you have to analyze each one in turn. Well, next time, we'll look at a related theorem called the law of cosines. And together, these 2 theorems will permit us to solve pretty much any triangle. Next time, we'll look at the case where we're given 2 sides and the included angle, or all 3 sides of a triangle. If we're given all 3 sides, can you find all 3 angles? Well, next lecture, the law of cosines will permit us to do it. The law of cosines generalizes the famous Pythagorean theorem. Great. Let me take a moment now to talk about some general issues of mathematics and studying mathematics. I think for success in getting ready to take a calculus class or getting a real firm understanding of pre-calculus, I think it's important not only to watch these lectures and hopefully enjoy these lectures, but to do the next step, and that is to practice. Please look at the workbook when you have some free time, and generally there are 10, 11 exercises per lecture that correspond to the examples I've done here in the lecture, and they kind of reinforce the ideas that we've talked about. Also in the workbook, you'll see a repeat of some of the important examples that we've developed during the lectures. Savor these examples. I like to tell my students to not only just watch the lecture and to read the examples, but to write them out fresh. Write them out as if you were learning them for the first time. I think I've mentioned before, but I'm a firm believer that as you're writing mathematics, a lot of learning comes up the arm and into the brain. Remember, math is not a spectator sport. You won't learn a lot of mathematics, I don't think, if you just watch other people do mathematics. Fine, it's fun to watch me, I hope. But the real learning takes place if you become the teacher, if you do the mathematics, rather than just observe me doing them. One of the things I require of my students, for instance, when they take my classes, is that they rewrite their lecture notes. So they go to class and they take notes from my lectures, and then I say, look, why don't you spend some time rewriting them? In fact, I encourage them to rewrite them in a group so they can talk among themselves about what they just saw in lecture. And what they discover is that as they're rewriting it, there are many points which they didn't fully understand during the lecture. And so that rewriting process triggers some good questions like, whoa, wait a minute. And then they can go back and look at the lecture, or you could go back and look at the video and say, oh yeah, that's what Professor Edwards said. He said that. And it makes that you develop a set of notes that can be very valuable as you move on and study more mathematics. So, enough talking about study skills in mathematics. I invite you to tune in for the next lecture. It'll be on the law of cosines. It'll be a lot of fun, and I can't wait to see you. Bye-bye.